Good afternoon. Can you hear me?
Yes.
Yes.
Okay, very good. We can start it. By the way, do the dog and the cat get along?
I think so.
Okay. Someone asked me to tape it, so I better find the key to tape it. Just raise the button. Raise the button to tape it. It's automatically taped. Does anyone know? Yeah, it's a recording. Okay. A little bit news about the final exam. The university set some policies for the final exam. And I want to tell you that we are going to honor the university policy to give the final exam during the university specified time. That will be Monday. Let me see. That will be Monday, May the 4th at 8 o'clock. Is this okay to everyone? Let me open the chat. That's a university assigned time. Our final at 8 a.m. Monday, May the 4th. It shouldn't have any conflict with other exams of yours, because university carefully designed it, and the dean and our chairs would like us to follow this policy. And it's going to be 3 hours exam. For those who need extra time, well, it's 3 hours. So officially, it's 3 hours. So we can start slightly early. We can, let's say, we can start at 7 o'clock. I can automatically release it. So Blackboard can release the problem at 7. For those who need extra time and have been approved by the university, I will give you extra 1.5 hours, so you can have it, the exam, until 11:30. That's a long time. But I don't intend to trouble you all the time. You should be able to finish the problem well before the allotted time period. Another major announcement is there's too much trouble with proctoria, not only in my class, both classes, all kind of problem. Password, high-speed internet, interruptions, web cameras connections, all kind of problems. And I think it's for this class, I have less problem. I don't have many problems. But the other class I had 63 students, and I really had a lot of problems. Student, I give you a whole day to take the exam. There are more than 10 students start taking the exam 10 minutes before 5. And all of them have problems. Internet connection, password. So, bottom line, this is a good class. So I intend not to use proctoria this time. I got approval from someone high up. So no more proctoria this semester. But I will release the exam problem at the 7. So for those who don't need extra time, you can start at the 8 or 7, but make sure you submit it within 3 hours. Is this okay?
Yes.
Okay. Any questions?
You keep mentioning like the exam problem being like it's one problem. Is it just like multiple problems on the final, or is it just a compilation of one problem with multiple aspects from multiple chapters?
I will give multiple problems, but maybe 3, maybe 4. I'm not going to occupy entire time of yours. Did I answer your question?
Oh, you did, yes. Thank you.
Okay. Any other concern about the final? If you don't have question about the final arrangement, we can discuss 2 items. One is the homework, the other one is the exam 2, if you have questions. Exam 2, most of you have trouble doing the linear regression for the first problem. And Ronald did it very, very neat. So I like him to share with you his exam. I have it, let me see. This is the first problem. And this is the solution I have. And but I don't have the detailed answer. This requires linear regression 3 times, not single time, not 2 times, 3 times. And Ronald did it very well, because if you see the data in our textbook, you see our enthalpy falls between these 2 data points and these 2 data points. And we know the pressure is 20 kilopascal. So it has to be between these 4 numbers. And the final temperature has to be between 100 and 200 degrees C. So if you got a number outside no, 150 degrees C. If you get the temperature outside this range, something is wrong. So Ronald did this very, very clearly. He stipulated the first law, eliminating unnecessary terms. He got the first law, this simple expression. Then he got the H for the exciting fluid. Then he did the regression 3 times. Ronald, you want to use your device to share with us the answers, your answer?
Sure, I can do that real quick.
Yeah.
It's saying you have screen sharing disabled for me, though.
You want me to project it, or you can project it?
It won't let me project it.
Okay.
It says you have me disabled.
Sure, yeah.
I guess you're going to have to do it from your screen.
Oh, I have to give you, oh, yeah. Okay, sorry. I forgot to do it. Now you should have,
Okay. All right. Let me. So let's see. So we ended up getting that 2,706 for our
Yeah.
enthalpy here.
Mhm.
And we know it's going to be in between the 100 and the 150 degrees Celsius.
Mhm.
So first we got to find the enthalpy at 100, which I called our low one, and then the high value, which will be in between the 150s. So let's see, for you do 20 kPa minus 10 kPa over the 50 minus 10. And then you put in the corresponding enthalpy values for those, which HE low is what we're looking for. The 2687 will be right here. And then you'll do the high value, which is 2682 minus the 2687. And that'll tell you what enthalpy for the low value at 100 degrees Celsius is at 20 kPa. And then you're going to be doing the exact same thing for the high value.
Mhm.
The only difference is now you're getting the numbers from the 200 degrees Celsius, which is 2879 and 2877. You do the interpolation and you'll get 2782.
Mhm.
And now the final interpolation we do using the HE that we solved for, 2706, minus the low value over the high value minus the low value will give you the temperature we're solving for minus 100 degrees Celsius over 150 minus 100, and that'll give you 110 and 8 degrees Celsius.
Mhm.
And that's all there is to that one.
Yeah, very good. So this HE low means the enthalpy at the low temperature. H sub E high means at the other temperature. Is that correct?
Yes, sir, that's right.
Okay.
Low is at 100 degrees Celsius and high is at 150.
Yes, excellent. Yeah. Any questions about Ronald's procedure? This is really neat. Okay.
Yeah. Sure,
So let me show. Share the screen. Yeah, take a look at what I circled. I use a pencil to circle all the numbers he used. And we can do linear regression. If you don't have a question, we can move to the second problem. Heat is provided to the two-phase, I believe. No, saturated vapor is initially stored. Heat is provided to the steam so that the steam expanded reversibly and isosomally to 0.8 megapascal. We are asked to estimate Q and the W. So we have two unknowns. Obviously, we have to use first law and the second law. Most of you got it correct. The second law, entropy balance and energy balance, we can generate the other equation. So Q is the quantity we can generate it, and then we can generate W from the first law. So after this point, I would say standard exercise of this course will be problems involving both first law and the second law. So be aware, I already give you a hint. Governing equation usually are the first law and the second law. Write down these equations, simplify the first law, you get this simplified first law, then you can find W. So most of you get the second problem correct. Any questions? If you don't have questions, we can just start discussing the homework problems. We have 5 problems, 5 or 6, 6 problems to be collected tomorrow morning. What problem do you like to see discussions? Can we, Mitch send us a message? Can we put the problems up for just a second longer the way we did it? the solution I share with you has the, I believe this is the file. So I'm taping it. I'm going to put this solution up so you can look at it. Okay, Mitch, is this okay to you?
Yes.
Okay. Yeah, you can look at the problem is exactly what I have during the exam. And here is the solution. This is short answers. Then I take in to the table, I circled the points I will need, and I confirm with Ronald's answer. This is very neat. So my answer is exactly the same, 110.8. I couldn't believe it, 110.8. So with this taped video, you should be able to see these two problems. Okay. So homework.
I have a question from the homework on number 1, just like a kind of like general question. For a reversible heat transfer process, isn't it also isentropic? So wouldn't delta S be the same as delta S total and delta SL? Aren't they all the same?
For isentropic process, yes.
And aren't reversible heat transfer processes isentropic?
Yeah. Isentropic means no heat transfer. And let me share the slide with you. Entropy balance equation. Let me see. Change in entropy equal to dq over T plus entropy generation. If there's an adiabatic process, there's no such term, no heat transfer. If it's a reversible, no entropy generation. So ds equal to 0, that means S2 equal to S1. Yeah, this is the integral form of this dynamic equation. We integrate from time 1 to time 2. Okay. Oh, I didn't share, did I?
Yeah, we didn't see what you.
Oh, sorry, I didn't share. Yeah, I was using this piece of slide to discuss the dynamic form of entropy generation, entropy change, entropy balance for a control mass equal to a term caused by heat transfer, then plus the entropy generation rate. Then integrate from time 1 to time 2, we get this expression. If there's no heat transfer, this term equal to 0. Entropy generation for a reversible process this is 0. Now, this is for closed system. Chapter 6 deals with a closed system. For we if we are dealing with a dynamical system, for open system, we have to look at different problems. Let me open chapter 7. We are still dealing with chapter 6 for this homework, but for open system, no, not this one. Many things are going on at the same time. 9, exam. Did I open? I thought I opened chapter 7. Chapter 7. This is it. Okay. For chapter 7, for open system, this is a coming attraction for next week. Entropy balance, you have to deal with this equation. It has 2 extra terms. These 2 extra terms are associated with the fluid coming into the control volume, and the fluid carry the entropy out of the control volume. If the control volume is chosen like this rectangular box. So next week, you're going to include these 2 terms for open systems. For the current homework, you don't have to worry about those 2 terms. Any other questions? Any particular problem you would like to see detailed solutions, or you have a specific question we can answer, then we can give you some hint how to solve the problems. Can you all solve number 9, 8 and 9? No questions? You can all do well. I think many problems involve the combination of first law and the second law. And then burn.
Can we do number 5?
Yes, I can do number 5. Number 5 is a nozzle. And let me read the problem. Air enter the nozzle at a given conditions, given the velocity. The air exit the nozzle at a given pressure and velocity. In addition to gas expansion, heat is transferred, released to the nozzle surrounding. Estimate T2 and entropy change. So if we are given velocity, definitely first law has to be used. First law has different form. Chapter 3 deal with closed system, has only one form, simple. Chapter 4 has 2 forms. One form for the steady state. The second form toward the end of chapter 4, we have a dynamical, no, not dynamical, the integrated form for transient state or unsteady state. So which one do we have to use? The equation in chapter 3 or the first equation in chapter 4 or the second equation for chapter 4? Any vote? By now this should be a piece of cake. Can you say we should use, by the way, nozzle, if we choose the control volume as the nozzle tip, does it have mass coming in and going out? Yes. I don't want to put the word in your mouth. I think we all stay home for too long. You all become people with social distance.
What's the question?
Is the nozzle an open or closed system? Let's say control value. This book uses the word. Can anyone answer?
Closed.
Did you say close?
Yeah.
Nozzle tip right here, the fluid goes out. At the other end, fluid comes in, pass through the nozzle, and get out. It has to be an open system.
It's open.
You agree now?
Yep.
Okay, now we agree it's an open control volume. Then can we assume it operates the steady state? Because chapter 4, now we know we have to go to chapter 4. Chapter 4 has 2 parts. steady state and unsteady state. Is this nozzle operated in the steady state or non-steady state? Unsteady state. Do I have a vote?
It's a steady state.
It's what?
Steady state.
Yes, very good. Does everyone accept the answer? It's a steady state because there's no hint. The nozzle is operated in the non-steady state. The fluid comes in, goes out at a steady flow rate. So what is the working equation and what is the working equation reduces to? How many terms will be in the first law? This is the way I tackle problems, okay? Make your choice about the control volume. Then choose the first law from the right chapters, from the right place. Then eliminate the zero terms so the equation simplifies significantly. Can,
Five terms?
I'm sorry,
Five?
five terms, you mean?
Yeah.
What are these five terms? You're
Well,
right.
First law, it's heat transfer,
Yes,
enthalpy in, velocity in, enthalpy out, velocity
Yes.
out.
yes, exactly. More specifically, the yellow marked term, yellow marked equation is the first law equation you should use. You agree?
Yeah.
Okay. Then within this equation, we found H2 is the only unknown. Other terms are given. So we can find H2. Question for you. If we know H2, do we know everything else for the exceeding fluid?
Yes.
Yes, we do know everything else. Because, let's see, yeah, because we know the final pressure. So if enthalpy is known, we know two parameters. And then from the table, we can find the temperature. You may need the regression. The temperature of my solution is 297.2 K. And entropy is 1.6924 kilojoule per kilogram times K. So that answered the first question about temperature. Then we have to use the second law to estimate the entropy change. total entropy change equal to entropy change of the control volume plus entropy change of the surrounding. We have examples in this slide. Do you all know how to tackle this? Let's say entropy change of the control volume. How do you estimate? Can anyone give us some hint how to approach entropy change of the system, both temperature and the pressure changes? And for an ideal gas, we assume this is ideal gas because pressure is not awfully high. But temperature and the pressure are fully given for ideal gas. How do we estimate?
Is this still for number 5?
Yes, I'm still working on number 5. Yes. It asks us to estimate delta S total. Delta S total, as you know, equal to look at the larger picture at the bottom of this part. It's the sum of entropy change of the control volume plus entropy change of the surrounding. That's how entropy change of total is defined. That also says entropy change of the universe increase all the time. And that's how many people use it. The entropy concept to describe the chaotic phenomena of the world. But this is people writing books on that. But this is beyond our course. Now, let me return to the slide I linked you. Let me see, number 7, number 6. If we know the entropy for state 1 and the state 2, if we want to estimate delta S, can we use this equation? You have to review the material, review the lecture, the video lecture. And this is one of the difficult part. Standard entropy is a function of temperature only. So that means this is a function of temperature. And this is a term that corrects the pressure change. So this is a useful expression for the estimation of entropy change of the fluid in and out. Okay. How about surrounding? Surrounding, we can use the definition of entropy. It receives certain amount of energy, right? Yeah. The surrounding receive Q. So Q is going to be a positive quantity divided by the surrounding temperature. Then we take the sum of these two entropy chains. You have questions?
Yes, sir. I have a question.
Yeah.
So for finding entropy, we use table 8.7.1 for ideal gas, but it is at 0.1 MPa. So does it matter the pressure
Talking
is
about the same
different
problem?
when we use this table?
Are you talking about the same
Sorry?
problem?
Yes, sir.
Can you repeat your question again?
So for finding entropy, we use table 8.7.1, which is on page 662.
Mhm.
But this table is for ideal gas at 0.1 MPa pressure.
Yes.
But for this question, we have two different pressure. And
Yeah.
how can we use this table? Like they are in a different pressure. I mean,
We use the standard entropy table. Standard entropy table on page 662 for air.
yes, sir.
I
But
haven't.
it's in different pressure. I mean,
Oh, that's why you need a pressure correction factor. So
okay, so this is for use the minus R times line P2 over P1, right?
this correct the pressure. Yes. This from,
Okay, I got you.
from the table. Yes. Did everyone follow? How does the videos help your learning? Do you understand about the same or much less or slightly less? You can give me some comment. Where it work? This distance learning, where it work? Or you totally give up already? No, no comment? Okay, any other problem you have questions? Oh, number 6. I was reviewing the problem statement and my answers. I think number 6, we should assume adiabatic. The vessel, rigid container is adiabatic. There's no heat transfer. So is number 6 open or closed system? If we take the control volume, the total container, even it has a partition in there, if the total container is considered the control volume, then it's a closed system. No fluid coming in or going out, no. We remove the partition, the material still stayed inside the control volume. So you say closed system. Then again, we can use first law. We can use the second law to answer the questions. Both first law and the second law have to be written down, manipulated to answer the question. You think you can submit the homework tomorrow? You must have some opinion.
I'm still kind of struggling to figure this all out. Is
With what? Struggling with what?
just like the homework in general. Is there going to be like a, I don't know, where we can like meet with like the
Which
the
problem?
DA?
Which problem you have trouble with?
Kind of all of them, where like I can start all of them and get to like a certain point, but then like there's always one point in a question where I'm just like I'm not really sure. I get like stuck. I can't get past that point.
Can you be more specific?
Like, all right, so earlier we were talking about question 1, and I was able to find or I think I was able to find the heat transfer. And then from there, like once you have the heat transfer, like
Problem number 1?
yeah, and so like you solve it with like delta S equals delta Q over T, and plus S gen. But since it's reversible and isentropic, S gen equals 0.
We have a Carnot cycle. Heat is released at the low temperature to the low temperature reservoir if the entropy change of the fluid is by definition, entropy change for a reversible process equal to Q divided by T. So for this problem, can you just say Q equal to temperature of the fluid times delta S of the fluid? Both are given. Temperature of the fluid is given.
Yeah, I got all that, but then once it tells you to find delta SL and the total entropy change, delta S total is supposed to be equal to entropy in minus entropy out plus entropy generated.
the other is, okay.
But as far as I can tell, there's no way to find those values. But
Okay. If so, the fluid side, you have no problem, right?
no problem.
Now the reservoir side, reservoir receive certain amount of heat, right? It receives certain amount of heat, and the temperature of the reservoir is given. So we just use the same Q, but divide by the low temperature reservoir's temperature.
Wouldn't that just give us the same?
No, it will not be the same because reservoir is at a temperature different from the fluids. Did you look at the slide? Let me route you to the slide of chapter 6. I believe we have a few examples at the outset. Let me see. You have to review the slide. I believe this is one example, but let's look at a simpler one. Make sure you understand this problem. I believe I also made the comments when I made the video. All these 3 examples have similarities. That is, if you want to calculate entropy change of the control mass, entropy change of the surrounding, their Q may be the same, but temperature are different. So we always create a positive entropy generation term. Okay? Look at this example, slide number 39. This is another example. A heating element receive electrical power, give away heat at the other side. So the problem involved taking the control volume 2 times and then analyze the entropy generation. This is a very important concept. This is the first example. First example, second one, third one, and this is a complicated one. So I remember in the slide, when I make the video, I explain entropy generation always caused by the temperature difference between the fluid and the reservoir temperature. Okay. So heat transfer is the key. Look at this example so you understand how to calculate entropy generation. The first 2 homework problems actually are related to this set of problems. Okay, I can share with you the problem, the solution for the first problem. So you can tell we calculate the entropy change of the fluid, entropy change of the surroundings, and sending up together, it has to be a quantity greater than 0. Oh, this is reversible, so this is 0. this problem, yeah, I'm sorry. Yeah, you were right to say yes. For a reversible process, it's identical. But I think the second problem, you don't get such a result. For the second problem, entropy generation is greater than 0. Any other discussions? So if you don't have further questions, does that mean you can submit the homework tomorrow? No comment? So can we have dinner now? No comment either? So shall we have dinner now?
Yes, thank you.
Sure, thank you. If you have any question, if you want additional sessions before the final, let me know. Okay,
Thank you.
sure. Yeah. Well, you take care of yourself. Oxford has been invaded by this virus. Yeah, be careful.